So this session, we will look into decision tree. This is one of the method yang kita guna untuk perform classification. If we recall back the method called k nearest neighbor, they're looking at the class of the nearest neighbor. Then they will assign the new item or the new data with the label the same as the nearest neighbor. It depends on how many nearest neighbors. So that's why they put k. So k could be 1 or 2 or 3 nearest neighbor. So they will look at the majority label of the nearest neighbor. So today we will look into decision tree. Okay. So decision tree will look something like this. It helps us to make a decision. So for example, in this diagram, they make a decision to accept the offer based on a few facts. So our decision tree learner built a model in the form of a tree structure. So basically we look at the root of the tree first. So in this example, we are looking at here. So if the salary for at least 50,000, if yes, then we go here. If no, meaning that we decline the job offer. Okay, and if the travel time or the commute time is more than 1 hour, if yes, meaning that you need to travel longer time, then you have to decline the offer. If the commute more than 1 hour or less than 1 hour, you go here. And if the offer the job offer free coffee, if yes, then you will accept. So the only way you accept the job offer is when the salary is more than 50,000 and you travel less than 1 hour and you have free coffee. So this is the tree structure or the decision tree form when you present the data to them. So the method will construct the tree based on some statistic or based on some calculation. We call it entropy or information gain. So what happened is the model itself comprises a series of logical decisions. So at each node, they will make decision to go to certain path. So at each node, they split into branches that indicate the decision choice. So some other you go left or right, or maybe you have multiple choices there. Okay. So for each tree that we have, they are dominated by the leaf node, which indicate the label. Okay, so this is the leaf. Okay, this is the class label. Whether we accept or do not accept the offer. So when we try to map this one into our data, so for example here we have the blue one is class 1, red is class 2. We can easily transform them into this tree, this decision tree. So it says that if the value of x1 is greater than W10, so which is this one, if yes, then you go here. If the value of x2 is greater than W2, which is up here, then we say this is class 2. Otherwise, this is class 1. And if you go here, of course, this is behind here, so this is the blue circle. So as you can see, we can transform this two variable data that we have, and we have binary classification. So we can easily transform them into decision tree. So we have two variable x1 and x2. So how do we actually split the data? How do we use the attribute to split the data? What is the best splitting? Sometimes, if you notice that we are using x1 first and then x2, why not we use x2 first and then here we use x1? So the choices of finding the best attribute to split the data will depends on the calculation of the what we call it information gain. Okay, information gain is a computation saying that if we split the data like this, it will give us more gain in terms of the information that we have. So what is this entropy or information gain? Okay. They use this probability. For example, we look at this group. Okay. So what we want to do is when we split the data, we want to have the leaf at the end of the tree have majority of them belong to same class. So if you want to have here, so what we want to have here, we want all those sample with this logical decision, all of them belong to the square red. And if I go from here to here, all of them must belong to blue circle. But sometimes we cannot fit all of them. So, for example, if we have this group, okay, so the group consists of 5A and 3B. The main objective is we want to split the data so that in that particular group we have all A's or all B's because they are more pure. So we want to maximize this. But we must have a mechanism to compute what is the value of this, purity of this. This is the purity of this group. Okay, so we will look into the probability. So for example, like this, for the class A, we have 5/8. And then for the class B, we have 3/8. So how do we sum up them together? So we will look into the weightage again. Okay, for example, like this, we are looking at if the group here consists of all same class, we will have 0. It means they are very pure. If they are not pure, meaning that they are 50-50 percent. The content of them is 50-50, so value will be 1. So we will use this what we call the entropy. So this is the formula of entropy. The formula of the entropy look into the probability of having that class in that particular group. So we will use this value. We'll use both this value. And notice that we are using log base 2. So how do we actually compute the purity of this? So we will make use of these two information. So the formula is you look at here by looking at class I up to K. But in this example, we have class A and B. So that means we have two parts. One is the class A, the other one is class B. So we just make use of this information. So we just plug in the probability of A. So we have 5/8 and 5/8 here. and then we also add the other class. So this is 3 over 8. So when we compute, we will get this value. Always careful. This is log base 2. Log base 2. So when we convert them, we will have this value and we add up them together, and this is the value. So the 0.95 here referring to how pure is our data. Since we have 5 versus 3, so we do not have a pure grouping. So the objective is to minimize this one. Because we say that if a particular group belong to a single class, then the value for the entropy will be 0. Otherwise, it will become nearer to 1. Okay. So let me give you another example. Okay. For example, like this. We have this table, and this is our class. So we will say, okay, we will play if we have certain conditions. So this is the independent variable we have, 1, 2, 3, 4. And this is the table that we have. So let's suppose we have this particular tree. So we are looking at the outlook here. So the outlook here, we have 3 attributes: sunny, overcast, and rain. Okay. So if we look at the sunny, we count how many no and how many yes here. Sunny, 1, 2, 4, 5. So we have 3 no and 2 yes. Okay, but if you look at the overcast, let me use different color. Okay, if we use the overcast, we have 1, 2, 3, 4. So we have 3, 1, 2, 4 yeses. So all 4 yeses here. If we look at the rain, so we take the remaining, so we get 3 yes and 2 no. So for each of these partition, we can compute the purity of that particular group. Okay, so if we use the outlook and attribute to split our data, so this is how we compute them. For example, we are looking at the sunny first. Okay, so this is the sunny. So we have for the no, we have 3 over 5. For the yes, we have 2 over 5. So we just plug in the number here, and we get this value. So that is the entropy, or measure of purity of that particular group of data. Over here, we have 4 yeses. So that means we have 4 over 4, log 2, 4 over 4. So this one is 1, log base 1, log base 2, 1 is equal to 0. So we will have 0 here. So meaning that we have 0 here indicate this is most purest group that we have. And if you look at this one, so this is 3 yeses and 2 no. It's similar to this, just this 3 no, 2 yes. So the value for this should be 0.96. So for this particular group, let me change first to yellow. So for this particular group, the entropy is 0.96. And this one is 0.96, and this one is 0. So the total entropy, we have to know how to combine all this total entropy. So we use the weightage. So we use the weightage. Okay, in this case, we are looking at total entropy should be like this. We use the pemberat here or the weightage. So we have how many data here? 3, 3, 4, 14. So over here we have 5. So 5 divided by 14. Times 0.96. Plus, this one we have 4. 4 over 14. The 4 here refer to how many member here. The 14 here refer to total data that we have. So this is times 0 because we have 0 entropy. Then plus, over here we have 5 also. So 5 divided by 14 number of data times 0.96. The total here will be the total entropy for the whole splitting. So meaning that at each group, we will compute the entropy. Then once we found all the value for the entropy, we will combine them by using the weightage. Okay? How do we actually use this information to compute the information gain? So this is what we have to look into. The information gain that we compute is this before splitting. Let me refresh that one. Erase first. The info gain that we get for the splitting will be computed based on the entropy before you split. Okay, this is before you split, and you minus after you split. So, meaning that if you go back to this slide, the total entropy after splitting will be this. Total entropy for before will be group of this. Let me show you the example here. Okay, this is just to show you that we split the data into partition. So the aim is we want to have all of the same label to be partitioned in the same group. Okay, this is good. The split for this one is perfect. This one we have a mix of them, so this one should be belong to the other part, and then this one should be belong to here. Okay. And this one also, this one is pure. This one we have a mix 3 versus 4. So we want to have this. And we say this is maximum purity or minimum impurity. Impurity meaning that they are not pure. Okay, so this is purest one. This is less impure, very impure. Okay, impure means not pure. Tidak, we call it purity. Having homogeneous label. Okay, this one mixed label. This one only a single label. So to calculate the IG, we are looking at this is before and this is after. So this is before, not this is the weightage of individual group that we have. This is the formula that we have. This is for each group, and this is the weightage for each of the group. I'll show you in another example. Okay, for example, like this. So we will use the same example just now. Okay, the info gain here is to compute the entropy before. So before will be around here. Okay, so around here meaning that we will compute entropy for all of this. So for this we have how many no? We have 1, 2, 3, 4, 5. So we have 5 over 14. Okay, so 5 over 14. And also we have 4 over we have um, 1, 2, 3, 4. That means we have 5 over 14 and 9 over 14. So that is our initial. How do we compute that one? Let me erase first. So here, the entropy that we get here will be, this is the entropy before, which is over here. Before splitting, we have all of this. Okay. So before splitting, we'll have, okay, minus, this is 5 over 14 log s2, 5 over 14 plus, okay, this is for the no. And then the second one is for the yes. We have 9 over 14 log 2, 9 over 14. Okay, what is the value for that one? Okay, so if I then can use the Google to compute. So we have let me share that one. If you don't have calculator, it's okay. So what we have here is that, okay, I have 4 over, no, 5. 5 over 15, 14. So this is for the no, log 2, and then 5 over 14. So I make to make sure I have this. So this one will give me this, but this is only for the no. So I need to add the yes again. So the yes, we have 9, 9 over 14, 9 over 14, and we have this. So value for this will be negative 0.94. So I take that value, I put in here. I share here. So basically the value is here minus 0.94, which turned out to be 0.9. So before the splitting, the value of entropy or the value of purity is 0.94. Let me change different color. And the value is 0.94 before splitting. So after the splitting, okay, this one will the value for the sunny, the entropy here, and this is the value for the overcast, and this is the value for the rain. To combine all this value, we have to use the weightage here. So put 5/14 here because we have 5 member here, and then 4 here to be 4 member here, and then 5 again, the 5 member here. And we plug in this value here, and we get this one. So this is the total of entropy or the total of measurement for the purity. So this is before and this is after. So this is before and this is before, then this is after. So when we minus, so that means this is the information gain that we have. So the objective is we want to maximize this. The more higher the value, the more information we gain. So meaning that the objective is want to make this smaller. The value of the entropy is smaller. So want to choose a splitting that will make all the value of the node to be purity will be very pure, which means almost to 0. So that's how they form the tree. They look at the information gain, and this is how they compute the IG or individual splitting that we have, and then how they combine them together. So that is what happened in the background. How do we apply this? So we look into this example where you see the slide. Oh no. So this is the. Okay. So we look at the actual application of decision tree when we want to apply this one to a new application to loan. So based on history, based on the data that we have, they will try to make a rule or try to generate a rule that easier for us to make decision. Okay. So the first thing that we need to do is we need to collect the data, and then need to prepare, and then we train the model, and then we look at the how do we evaluate the model, and then how do we improve them. So we get the data from this UCI machine learning data repository. So they have this loan application. Okay, so when we read the data credit.csv, so we're reading the data here, and then when we look at the structure of the data, we have this one, the default. Okay, so the default means the default is yes, meaning that they are not paying the credit card. If the default is no, so meaning that they will pay the credit card. So basically, this is your label. This is your label. Based on all this information we have, like the checking balance account, how many months you on, the credit history, amount on, saving balance, employment duration, percentage of income, and so on. All this, the system automatically a feature that they can use to split the data, and it will give you the best model for predicting whether the new applicant is able to pay the loan or not, and they can approve the loan. Okay. So first they're looking at the checking balance. So the checking balance, we have this number of so this number meaning that there are some missing data here, so the unknown. we also have this value 269. This is number of people who has less than zero Dutch money. This is the number of people who get more than 200 Dutch money. And this is the number of people who get between who has 1 to 200 Dutch money. And we are looking at the saving account, the saving balance also. This is the checking balance. This is the saving account. So we have 600 over who has less than 100 Dutch money. We have 48 only that belong to those who have money more than 1,000 Dutch money. We have 103 those people who has money between 100 to 500 Dutch money. And we have this amount of people who get or who has money 500 to 1,000. And this is unknown. Okay? So the unknown means they are noise. So we also look at the summary for the month loan duration. Okay, the minimum month loan duration is 4 months, maximum is 72, meaning that they have 5, how many? 6 years. 5 years is 60 months, so this is 6 years. And this is the amount of loan that they apply. So this is the minimum 250, and this is the maximum 18,420. So the function summary here is just to give you a descriptive statistics of certain column that you have in your data set. This is performed for the amount. This is performed for the month loan duration. And we can also use the table to look into the percentage of people who default, meaning that 30% of all time people will not pay the loan. So if the default yes means they not paying the loan, and if the default is no, meaning that they pay. So that means all the applicant that you have, 30% of them will not be able to pay the loan. So this is based on your data in your database. So based on this distribution or based on this data, we want to model a decision tree in such a way that it gives us a guidance on how to evaluate new applicant. So based on history, the bank information that they have, so they will be able to tell whether they pay or not. Okay, now we look into how do we prepare the data. Okay, remember that we need to create the training and test data set. Okay, so your data here, so we will split them into training and testing. Okay, the training is used to train the model, and the testing is used to evaluate the model. So step.sheet, this one will ensure that you will get the same random number if generated by the system. So you can repeat the same experiment to compare the performance. Okay. So in this case, we will use the sampling method. So sampling means we will get the 900 sampling from the 1000. So meaning that we get 90% of the data randomly selected from your main data. So what happened is that, okay, you will take the 900 sample here and you put in the credit trend, and then the remaining will be in the test. So over here we only have 100 samples. Then if you look at the proportion table for your training data set, Okay, you still maintain this percentage, 70% default no, 50% default yes, meaning that you have a good distribution of no and yes. So similar to your test, so you will have the same also. So it's very important to use this sampling using a random selection, because we want to ensure that we have the same proportion for your training and also for the testing. So how do we call this decision tree? So first we need to install this library called C5.0, and then we upload into the memory. Okay. So what we need here is this is the model that we will produce. This is the C5.0. We call them. We give them the training dataset. We give them the class, and then the trial here tell you that you only need to form one tree. So if we get the okay, so this one we are looking at. Okay, I will give you all the data I have except the last column, because the last column is the default column, class label. So we do not want to have that one there, because we will put them in here. So this is your training data set. This is your data, and this is your label. So what happened here is that you training the model called credit model using the training data set and also the class label for 900 sample that we have. Once we get that one, you type this one, it will tell you the tree. So the tree will looks like this. This is your decision tree. So it says that if your checking balance is greater than 200 Dutch money or unknown, you are highly default, meaning that you will pay. So this one tell you how many record correctly classified and how many record that is incorrectly classified from the training that you have. And here, if your checking balance is less than 0 or between 1 and 200, and also your credit history perfect, very good, or meaning that default no, yeah, default yes, meaning that you wait, maybe I have the picture. Okay, this is the conclusion that we have. Let me see. Okay, if the checking account is unknown or greater than, then classify as not likely to default. Not likely to default. Okay, so if your checking account is greater than 200 or unknown, you are not likely to default. Yes. Otherwise, if the checking balance is less than 0 or between 1 and likely to default. Betul. So di sini you are likely to default, that you tend um, to pay the loan. So this is the conclusion that we can make from here. So this is very straightforward for anyone who look at this tree. So easier for them to make decision. And it also have a few more down here, so they can elaborate more. Then I will show you. this is the rule that we have. Okay, if you want to evaluate them, so remember that we have 100 of them. So what happened here is that we use the same model here, the same model, perform the prediction, but we are using the test data set. So when we try to look at the cross table, okay, so this is okay because the actual value is no, and they are predicted as no also, and this is okay. This is not okay because they are actual default is yes, but predicted as no. So this is so our error will be 2700. So the accuracy will be 100%, minus 37%, which is 73%. So this is the accuracy of your model. But there is a way on how we can improve this one because they call it the adaptive boosting, meaning that we can form many trees. So when we form many trees, the trees will become forests, okay, random forests. So how do we do that? We say, okay, I will do 10 trial, meaning that I will build 10 trees. So if I compare the performance of these 10 trees, the one, okay, now I only have how many error? I only have 18% error only. And my accuracy will be 82%. Because 100% minus 18%. How do I know? Because I get 18 plus 5, 18 out of 100. So let me show you how actually we perform this. Let me stop this video first, then I will share you the nail. Okay, I share you the one. So the first thing that we need to do is we need to upload the file, but make sure you are in the right directory. So how do you ensure that? I go to session, I go to that working directory, push directory. I put my data in the D drive. So here I will set my working directory to be D drive. Then I will read my data. So this one will read this data credit.csv from the working directory from the D, and I say all the character remain as character. If I look at the structure of my credit, yeah, so I have 1,000 sample, I have 17 variables. So when I say string as factor to be true, meaning that all the factor will remain the same, otherwise they change to character. And this is the one that label likely to default or not likely to default. Okay, so next what we want to do is we want to let's take a look at the sample, the percentage of distribution we have. So we have no 700 and yes 300. And then what we do the sampling. So we say this, and then we say, okay, from the 1000 sample that we have, I will only select 900. So if I look at the content of this is basically a code ID, the 900 of them. So basically, this is the raw number. The raw number. Okay. So what happens is that I will only select this raw number to be put in the thread. Okay. So I take all this raw number. From the credit, I will take all the raw number here again. So if I look at my credit, these are all the raw number selected. The 415. See this one. This is 415. Raw number 415, 463. So they will select only this 415, 463, and so on. And for the remaining, if you look at the command here, it will be negative because we'll to exclude all of this, and I will only take the remaining. So the remaining is only the 100 which are not included in here. So I will only take here. So we have to divide them. So if you look at the proportion of sample that we have for the credit and the test, so we have more or less the same 70% and 30%. Now we install the package. Okay, this is the C 5.0. This is also known as the decision tree. Okay, and then I upload into memory. Okay, and I will use that one to model this credit model. I call this model decision tree, and I will include all the column except the last column, because the last column is the label column, and the label I put here. So if I type the credit model, so this is what I get. No, I need to type the summary. Summary of my credit model. So these are the three that we have. So easier for you to refer here. If we say this one, the checking balance is greater than 200 unknown, so you are not likely to default. But if you checking balance is less than 0, between this, and your credit history is perfect and very good, and your housing is, and if you're renting, or you're renting, and you are your account is highly to be default. So this is 16 correctly classified and one is incorrectly classified. So you just follow. If you have new data, so you will have to follow the path here. So depending on the value, you can say no or yes. Okay, this is the tree that being constructed. So how do we evaluate them? So we will use the prediction. For the prediction here, we will use the model to perform the prediction. So predict using this model, and we will use the test data that we have. So the result will be here. So we will table out that one. We'll perform this, which means that we will look at the test fault versus the predicted one. We get that one. So meaning we have, oh, this is worse. This is 30%. 30% of error. Because we have this and this. Why this one give you different result compared to the previous one in the slide? Because when we generate the random number to select the training dataset, they use different initiator, means different random number. Okay. How do we improve this? We build many trees. So for example, here I'm using, and then I use that one to perform this one. I use to perform the prediction again. And then I will plot the table. 30 also, 13, 30. So if I could repeat them, okay, now let's say I'm using 50 trees. So 50 times I construct the tree. And then if I cross table using this 50, I will get 50 is here. This is using training. Train that one using 50, and this one is produce 50. Let me check again. Okay, I'm using this one to be, I'm using 50 here. File, no problem. Then I will use this one to predict. So this is 50, this is 50, and then I can perform the tabulation of the table. So, when I use 50 trees, I only can improve the accuracy by 1%. Because over here I have 20 plus 9, 29% error. So I suppose I want to try again. Okay, I want to train this one using 100 trees. Okay, and then I will perform the prediction using the 100 trees that I have. I forgot to change the name here. But this is 100. Then I perform the prediction using this 100. So I redo this one using 100. And then I compute the using the 100. Okay, so managed to improve the accuracy by 2% only, but it's okay lah. So there are so many choices setting that we could have. So that's how we perform the classification using decision tree. So any question?